Hi, today I'm going to explain how to use a sine wave with 1 Hz frequency to compose a square, triangular, and sawtooth wave and plot each harmonic and approximated wave by using Scilab. First of all, we can find the square wave equation in Wikipedia, which is the summation of sine 2 pi 2k minus 1 times ft divided by 2k minus 1 from when k is from 1 to infinity. After that, we can multiply by 4 over pi. So this is the equation of our square wave. So due to the time constraint, I have write the codes so that we can make it more clear and faster. So first of all, we need to declare pi, which is 3.142, and set the frequency of 1 Hz, f equal to 1, and set the time range from t to t is equal to 0 to t is equal to pi, and each division is 0.05. 0.005. So we need to declare a variable which is x equal to 0 and use a for loop to do the summation of sine wave, which is the sine wave of sine 2 pi 2k minus 1 times ft divided by 2k minus 1. So to make it to make the sine wave is more nearer to the sine wave, I have made the k is from 1 to 80,000 so that the graph is plotted more nearly to the square wave. So the square after that after we do the summation of sine wave, we need to do the we need to make the final equation of square wave, which is 4 times x over pi. X is the summation. So after that, we need to plot a graph by using plot t and the wave. So and we name the graph as the title square wave. So I copy this and paste the coding into the Scilab console. And what we see is a square wave is plotted. So by this is a square wave, a nearly perfect square wave. And next we're going to explain about the triangle wave, which is which is which is have Wikipedia also. The triangle wave has an equation of summation of minus 1 to the power of k and times 2 sine 2 pi 2k plus 1 ft divided by 2k plus 1 square, from k equals to 0 to infinity, and times 8 divided by pi square. So after expansion, the equation will be like this and can be expanded furthermore. So next I going to show the triangular wave coding. So first as usual, we need to declare pi, declare the variable, and set the frequency, set the time range, and just basically it is the same with the square wave. equation, but we just substitute the square wave equation, which is we just only to change this part and plot the triangular wave. So that let's see, compute and run this coding, and okay, the code is here by here, so wait for the execution. After the execution complete, it have show the triangular wave, which is like a zigzag. And next is showing a sawtooth wave, which is this. This is a sawtooth wave. It also have a equation in Wikipedia, which is sawtooth is equal to a minus 2, which the a is a constant, can be any value. It means the amplitude. So the sawtooth wave is equal to a divided by 2 minus the a divided by pi times the summation of minus 1 to the power of k times sine 2 pi k f t divided by k, from where the k is from minus 1 to infinity. So we use the sawtooth wave is this, just as the same like before, square wave and triangular wave. We need to add one, but this sawtooth wave we need to add one more a, which is the amplitude. In here I add my amplitude is 5, which is my constant is a number of 5. So as usual, we change the summation equation of sine of sawtooth wave into the x here, and we change the final wave equation of sawtooth wave in the wave equals to a minus divided by 2 and minus a times x, which is x is the summation part, and divide by pi. So this is very easy, and we just copy the codes and paste it into our Scilab console. First of all, we need to clear clean screen to make it clearer, and we paste it and just do the execution. Okay, this is a sawtooth wave. It's like the Wikipedia answer. Sawtooth is like this. So first of all, I have present all about the square, triangle, and sawtooth wave, and next I'm going to show using a Scilab to console the following. Something is load the wave file, which has recorded just now, which is explain introduction about my name, and load it into Scilab console and plot the sound signal by using the plot command, and print the and display the wave file sampling frequency and the bit rate. So due to the time constraint, I have written the code, so I just explain about it. For using the read the load the audio file, we need to use a y, has a variable y, has a fs, which is the sampling frequency and the bits per sample, and read the file wave read from the user desktop audio wave file. And after that, we need to display the frequency by using the command disp. This here is display the fs, and the title, the sampling frequency is fs. And next we need display the bit rate. First of all, I have displayed the bit per sample first. So the using the same command disp, which is bit display the bit, and bit rate is equal to the bit per sample times the sampling frequency. So next we need to display the bit rate is disp bit rate display bit rate. And next we plot the sound signal by using plot 2D of the y. Y is the signal, and the 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 value is 1 minus 1 to 1, and here is space because it's just do along from start till the end of the sound signal. And we name the graph the sound signal graph. So copy and paste into our time console. Copy and paste into time console. After execution, we have know that read the audio file have read and display the sampling rate. The sampling frequency is same to the sampling rate. The sampling frequency is 11,025 hertz, and we display the bit per second is the 16 bit per the display the bits per sample. The bits per sample is 16 bit per sample. So the bit rate equation is bit per sample time the sampling frequency. So next we display the sampling frequency is 176.4 kilobit per second. So we plot the sound signal, which is this, the sound signal. So here is our sound signal. Wait, I do it again to show the sound signal. The sound signal from 1 to 1. Here is our sound audio signal, and that's all from me. Thank you for watching.